Hello, class. So on this video, we're continuing on or I guess starting on section 3.7 because on the previous video, I was talking about the exam. So what are we going to do on section 3.7? Well, we're going to talk about this topic, which is called simple harmonic motion. So what's simple harmonic motion? We'll go over a specific example that demonstrates what this sort of motion is. The example we're going to look at is a spring mass system. So basically a spring with a weight or mass attached to it. It's the canonical example, meaning that it's the example that you usually see in all of the books. If you see this in engineering classes, you're probably going to see a spring mass system. But it's good because it demonstrates the properties that of simple harmonic motion that are important. Well, having said that, it's more general because simple harmonic motion has to do with motion that follows an oscillatory, what would you say? I don't want to say motion that follows oscillatory motion. So motion that follows an oscillatory pattern. Right? So oscillatory, think of oscillations. So what's an example of something that would follow an oscillatory pattern? Well, think of a guitar string. This is another example. If you pluck a guitar, well, first of all, your guitar string before you pluck it, looks something like this. Right? So it's the horizontal line. If you pluck on it, right, so you come here and you give it a pluck, let's say with a finger, what happens? Well, your guitar starts to vibrate. So let me see, it's just one possible way it might look like at a certain point of time. And the guitar basically is going to be doing vibrations, it's going to be going above and below this equilibrium state where it's not moving at all. Right? So it's going to be vibrating. And then this is how the guitar string might look at one particular point in time. At another point in time, it might look something like this. So above the equilibrium position or in its initial state. Right? So if you were to graph the position of this string, so let's say the position of this point on this guitar string after you pluck it, what would it look like? Well, let's say this is let's call it XT plane because we're going to try to model the position of a point as time passes by, right? So the independent variable, we want it to be time, so we're going to use T. And for the dependent variable, it's common to just use X instead of Y. I don't know why, but we're going to be using X. So what would the position of this point on this guitar string look like as time goes by? Well, as I mentioned, it's going to be moving above and below its resting state. So think of the t-axis or the horizontal axis being the guitar in its original state when it's not moving at all. Right? So you give it a pluck, it starts to vibrate or move above and below its equilibrium state, and the graph looks something like this. So any motion that looks like this is oscillatory motion. So that's what we're going to try to model. Given a system where you have something that's moving in an oscillatory pattern, is it possible for us to give a function that gives you the position of that object? So for example, the position of this point on this string. Okay, so this is one example. It's like one of the most trivial examples I can think of. And again, we're going to go through a spring mass system to see how it works more precisely. Let me say that there's a lot of other applications. There's a lot of things that follow an oscillatory motion, right? So think of the shock absorbers in your car. So basically, the wheels in your car have shock absorbers. So basically, if you hit a pothole, that shock absorber is basically contracted, and that takes or tries to take away as much energy or force from you hitting the bump or the pothole as possible, so that you don't feel it too much in the car. And then what happens to that shock absorber? Well, it stretches back to its original state, right? So that's, if you think of plotting that motion, you'll see that it looks like an oscillatory pattern. There are other examples, but in general, this is what's happening. And it's called simple harmonic motion because there's one assumption that's key to us being, or for us to be working with these models. I'll talk about what that assumption is. However, let me say that you can generalize this. You can generalize these this simple harmonic motion to just periodic motion. So just some sort of pattern that keeps repeating. Okay, so think of sine functions and cosine functions and other sort of functions. You can actually construct functions that repeat just by construction. You could plot a line and then on a certain domain, and then say, okay, I want this function to repeat, so just keep plotting this line in different domains, right? So there's some sort of periodicity or some interval in which the function always repeats, right? So simple harmonic motion has a key assumption that makes it simple harmonic motion, but it can generalize to just periodic motion in general. And periodic motion at its core is one of the most important applications of any field of applied mathematics, whether it's engineering, whether it's chemistry, whether it's physics. Okay? So what's happening with simple harmonic motion? This is going to be a good introductory example to periodic motion in general, right? And then once you get to your more advanced classes and you start doing Fourier analysis, you're going to be able to model periodic motion in its more general sense. But everything's going to build up from what we do here in simple harmonic motion. It's going to be very similar. Okay? So this is going to be a good introduction to a very important problem and family of problems that model a wide range of things. Again, anything that oscillates or that's periodic, you're going to try to model either with simple harmonic motion or with Fourier analysis, which is like an extension or generalization of this. So that's the introduction. I want you to know that this is a very important application. And even though we're going to be looking at this particular one with a spring mass system, it generalizes to a bunch of other applications. It's in terms of what we're going to be covering in the class, this is probably one of the most important things, at least application-wise. So I sell it a lot because I want you to pay attention and understand that. If you can understand this, it's going to make your life easier when you get to your other engineering classes and higher level courses that you take. So with that introduction out of the way, I'm going to, again, focus on one particular example of simple harmonic motion which is a spring mass system. Right? So what is a spring mass system? And I've drawn a couple pictures here, which I've labeled picture 1, picture 2, picture 3. And what I'm going to do is I'm going to explain each picture as we go on, and then we're going to see, what is it that we're trying to model. Okay? So the setup is this. We're going to have a fixed object or surface, right? So a surface that's not going to be moving at all, right? So that's what I've drawn in each of these 3 pictures as this horizontal line that looks like black with purple on top of it. So I drew on it twice for some reason. Okay? So it's going to be a rigid fixed surface. Okay? On that surface, we're going to attach a spring, right? So what's a spring? Spring is this sort of elastic thing that when you pull on it, it tries to go back to its original state. And in fact, that property that when you pull on it or push on it or contract it, it wants to go back to its original state. That's the assumption that we're going to be using. That's the assumption that makes it this simple harmonic motion rather than just more general periodic motion. Right? So simple harmonic motion is an example of periodic motion, but not all periodic motion is simple harmonic. So again, the key assumption is that you're working with some sort of medium. It could be a spring, it could be a string, it could be any other sort of medium. But this medium has to have the property that when you either stretch it or compress it, there's a force that's trying to get the spring, string, or whatever medium it is that you're working with to its original state before you stretched it or compressed it. Right? So that's the assumption that makes this simple harmonic motion. Okay? And again, not all periodic motion follows this assumption. Okay? So going back to the picture, we have this rigid surface, then I attach this spring, right, so the spring has its own weight, so it weight stretches it a little bit, but eventually it reaches this position where it's basically fixed. It's not moving anymore. Right? So that's picture 1. Of course, this is not a very interesting setup because nothing is happening. So what we're going to do is we're going to attach a weight to this spring. Right? So let me say that I'll probably say spring and string interchangeably, not on purpose. I'm actually trying to say spring all the time, but as I'm talking, I might change the P with a T. So if I say spring or if I say string, think of it as interchangeably. Right? I'm talking about this red thing that I drew here. Okay? So again, a spring attached to a rigid surface on itself, nothing much is going on. So what we're going to do is we're going to attach a weight to this spring. So as you would expect, when you attach a weight to this spring, it's going to stretch it downward. Right? Why is it going to stretch it downward? Well, because there's a force on this weight. Right? What's the force? Well, it's the weight itself. Right? So I'm calling the object a weight. Right? You can call it a mass if you want. I'm going to be calling it a weight. But you can think of weight and mass as names for this object as being interchangeable. Depending on the literature, some things might call the object mass, other literature might call the object weight. So I'm going to be calling it a weight. So when you attach a weight to this spring, again, there's this vertical force pushing downward. What? It's the weight, right? It's mass times the acceleration due to gravity. So it's obvious to think that when you attach the weight, it's going to stretch the spring. What is also obvious but not as easy to explain is why does the spring stop being extended, right? So we attach the weight, it stretches the spring, but it eventually stops stretching, right? Eventually stops stretching at a point and it rests at that point, at that position. Right? So maybe it's not as obvious to explain why it stops stretching and reaches a state where it's at rest. Well, one possible reason could be that the string is just reached as much as it can be stretched, right? That's not a very interesting reason. So let's assume that that's not what happened. And the way I drew it here, you can see that the spring is still coiled. So think of it as saying, okay, it's not that the spring has been completely flattened out. Something else is causing this weight to stop stretching the string. So what is it that's causing this? Well, what's causing this is the force that I mentioned, right? So we're assuming that this string has some force, right? That whenever you stretch it or compress it, it wants to go back to its original state, okay? We're gonna call this force a restoration force. Depending on the literature, it might have different names. It could be called spring force. It could be called restoration force, which is what I'm gonna be using. It also could be just called the spring stiffness. Okay, or sometimes the spring stiffness might be another thing, but I think those three names at least could be used interchangeably. I'm going to be calling the force a restoration force instead of spring force or the stiffness of the spring. Okay, so what's happening? You can see in picture 1 that the spring has a natural resting state, right? Basically, this state here. So what happens when you attach a weight? So I'm assuming that this weight is stretching the string S units. Right, so that's what I drew here in blue. So think of the units being, I'm going to be thinking of them as meters because I'm going to be using acceleration due to gravity as being negative 9.8. Actually, let me not say negative. That's going to be different, but 9.8 meters per second squared. But in general, it could be whatever unit of measurement you're using, whether it's inches, kilometers, etc. Again, I'm going to be using meters. Right. So in picture 1, we can see the original state of the spring. When we attach this weight, and this weight stretches the spring an extra S units past this resting point, what happens? Well, the spring has this restoration force that wants it to go back to its original state, how it looks in picture 1. Okay. So that balance between the force pushing downward, being the weight of the object, right, being the weight of the object, compared to this force or restoration force of the spring wanted to go back to its original state as it is in picture 1, those two forces balancing out, that's what causes the spring to stop stretching. Right? And let me mention here, since we're dealing with two forces, one going in opposite directions, it's important for us to distinguish between positive direction and negative direction, just like we did in the example of the falling rock. Right? In the example of the falling rock, since the rock was falling downward motion was positive, right? And then upward motion was negative. And same for the forces. Right? In this case, we're going to say that forces going downward are positive and forces going in the opposite direction, in this case upward, are negative, right? So the weight, a force that's pushing the spring or stretching the spring vertically downward, is going to be positive, and the restoration force of the spring, which wants to get back to its original state as pictured in picture 1, is acting opposite to the weight, and since the weight is going vertically down, the restoration force is going vertically up. And again, that would mean that the restoration force is going in the negative direction. So that is why the weight balances out. That's why the spring stops being stretched out by the weight at some point, because there is a balance of the weight and the restoration force of the spring, right? So those are at least two forces that are acting on this object, right? And there could be other forces acting on this, but I don't want to talk about that. As of now, these are the only two things that are going on, and that's why there's a balance. That's why the string stops being stretched by the weight. Now, we're going to be focusing on picture 2 and then moving towards the right. So we're going to forget about picture 1. I only drew picture 1 so that you can see what the restoration force of the spring is trying to do, right? The restoration force of the spring is trying to go put the string back in the same state that it is in picture 1, right? Okay. So we stretch the spring, right, S units compared to where it was in picture 1. And now this is where, not where we're going to start, but this is going to be the start of what we're going to be doing. Okay. This, as we're in picture 2, is still not a very interesting system. Why? Because there is no motion, right? We've reached an equilibrium position, right? And from now on, every time I say equilibrium position or equilibrium state, I'm talking about the state in picture 2, right? The equilibrium that is reached after the weight is attached to the spring, and then the forces balances out, and then the string is not stretched anymore. Okay? So that we're in equilibrium. There's no motion, so it's not very interesting. Again, if you go back to the picture or example that I did about the guitar string, what we want to model is the motion. You can think of it like this: the motion of a particle on the string as the string vibrates above and below the equilibrium state. So we kind of want to do something similar here. In this case, think of the particle as being where the spring touches the weight. Depending on how you draw your model, it might be different. Some people draw the particle at the center of the object of the weight. I'm just going to draw it where the spring meets the weight because it's the one that's easier to label. Okay. So this particle right now is in equilibrium position. It hasn't moved anything at all because we're in equilibrium, right? There's no motion in this object. So in the case of the guitar string, we pluck the string so that there would be some motion on the in vibration or oscillations on the string. What are we going to do to cause there to be motion on this system? Well, what we're going to do is we're going to pull on this weight, right? And that's what I drew in picture 3. You can see that there's a hand there, and that's basically mimicking the fact that I pulled on this spring, and I pulled an extra X units. And again, this could be in meters, in inches, whatever unit you're working with. For this case, it's in meters. So I pull. And it doesn't matter if you pull or push. So if you contract or stretch the spring away from its equilibrium position, it doesn't matter, right? What matters is that we want to give some motion to this system, right? So in this case, I'm drawing it like I'm pulling, right? So I pull down on the spring, and that's the hand pulling on the weight. And now the spring and the system is not at equilibrium anymore. Because what's the equilibrium position? Well, the equilibrium position is right here, when this particle is right here, right? When the weight of the object is balanced with the restoration force of the spring. So here, the particle is all the way down here, so there's not a balance. Right? So what's going to happen? Think about what could happen here if you let go of the weight. What's going to happen is, again, the restoration force of the spring is now going to try to pull back the object until it's back to its equilibrium state. And again, remember, now when I mention equilibrium state, I'm talking about the picture in 2. Forget about picture 1 now, right? So equilibrium state means state 2. Yeah. So think about what sort of motion that is going to do, right? So you let go of the weight in picture 3. It's going to go up, it's going to go down, it's going to go up, it's going to go down. And depending on what assumptions we have, it's either going to go back to equilibrium or it's going to stay moving up and down, right? So what's that motion going to look like? So I drew an XT plane here. So what is that motion going to look like? Well, it's going to look something like this. Right? Think again of how the particle looks like as time goes by, as this weight is moving up and down, trying to reach its equilibrium state, if it ever reaches it. Okay. So you can see that the motion of this particle on this weight, where the spring is attached to the weight, if you think of tracking that as time goes by, this is showing oscillatory motion, right? You can see that I drew the picture there. So what are we going to try to do? What we're going to try to do is we're going to try to model the position of this particle once we let go of the weight. We're going to try to come up with a differential equation that gives us, whose solutions are position functions of this particle as functions of time. So for example, you could say at time 3, my weight is going to be, or this particle on my weight is going to be all the way up here, for example. That's what we're going to try to do. Okay, that's the setup. Now, of course, the question is, how do we model this? Okay, how do we model the position of this object? How do we derive a differential equation that gives us solutions which are the position of this particle? Well, there's a way to do it, and it's not going to be that hard. Just let me say one more thing, which is kind of counterintuitive, but it's just the way it's done in the book and usually in the literature. When our object or particle is below the equilibrium position, we're going to say that it has a positive distance, right? So it has a positive displacement, right? And that's kind of counterintuitive based on the way we drew the picture, right? Because okay, we're below, so we're further down, but we're thinking of that as positive. But sometimes people draw this picture horizontally, and then it makes more sense. But again, in the literature, this is how it's done, and this is how it's done in the book. So when the particle is below equilibrium, we're going to say that its position is positive. On the other hand, when the particle is above equilibrium, so let's say our particle is somewhere up here, kind of like what I drew in this case. Actually, no, forget about that graph. Somewhere up here. So this graph is actually flipped, right? Because here our motion it's saying that it's positive, so that means that we're actually below, right? The equilibrium position. So it's kind of flipped, right? So if our particle is below equilibrium position, think of it as being positive displacement. So it's a positive value. If our particle is above the equilibrium, it's a negative value. So below, positive, above, negative. And when you graph it, you're actually you're graphing it kind of flipped about or rotated about the horizontal axis, right? So when my particle is here, so below the x-axis, I'm actually saying that it's starting above, right? Above the t-axis, sorry. It's starting above. So again, because when it's below the equilibrium position, it's positive. And then, as I mentioned before, I think I mentioned we're going to be using the independent variable t and the dependent variable x. So basically, we're looking for functions x of t that give the position of this particle as time goes by. Right? And then here is just a summary of what I said. If x is greater than 0, the mass is below equilibrium position. If x is less than 0, the mass is above equilibrium position. So that's the setup. Right? So at t equals 0, that's going to be the time where we let go of this mass, of this weight. And then as time goes by, we're going to see how this mass oscillates, and then we're going to see how this particle then is moving as this mass does whatever it does. And as I mentioned, depending on what assumptions we choose, this mass could either go back to equilibrium eventually, or it could actually just oscillate indefinitely without ever going back to its equilibrium position. Right, so we're going to see what those assumptions are. But this is the setup. So I talked a lot, so you can see how this how everything is being derived. Right? So hopefully that makes sense. If it doesn't make sense, please send me an email or come to my office hours. But if you just want to generalize it, we have a weight on a spring. We want to pull or push on that spring and see how it's oscillating and see what positions we get.